Hi everyone, in this problem we're going to evaluate this definite integral. So it's the integral of dx over 4 minus x squared from 3 to 5. There's a couple ways to do this problem. You can use partial fractions, and that's pretty easy. We're going to do it a different way. We're going to do it with a formula, one you may have not seen before. So the formula we're going to use is a very peculiar one. It's the integral of du over 1 minus u squared. And this is equal to the following. So you actually have two cases. So case one, it's equal to the inverse of the hyperbolic tangent of u plus c. And this will be valid if the absolute value of u is less than 1. The other case is it's equal to the inverse of the hyperbolic cotangent of u plus c. And this will be valid if the absolute value of u is greater than 1. So our goal now is to take this integral and make it look like this one so that we can decide which formula to use. So first note this 4 is a problem because this is a 1 here. So we can pull the 4 out from the bottom and basically write it as a 1/4 on the outside. And so we're going from 3 to 5 dx over, and this is 1 minus, and if you pull out a 4 from the x squared, it's x squared over 4. If you think about it, when you multiply the 4 through on the bottom, it cancels. We're still not there though. This is equal to 1/4 definite integral from 3 to 5 dx over 1 minus, and then this is x over 2 squared. Okay, x over 2 squared. So now we can make a u substitution, right? We're trying to make it look like this. So let's do that. We'll let u be equal to x over 2. So that means that du, well, the derivative of x is 1, so we just get 1/2 left, dx. There is no 1/2 in our integrand, so we need to get rid of this 1/2. So we just multiply both sides by 2. So we get 2 du equals dx. And now we can start to make the substitution. So we have the integral. So I'm going to replace this dx. So this dx is just 2 du. So I'm going to pull that 2 out. The 4 stays, and we have our du. So all we've done so far is replace the dx with 2 du. You see 2 du dx, and the 4 is still there, over 1 minus u squared. So what about the limits? Well, we made a u substitution, so we're supposed to change the limits of integration. So let's do that. So let's do the upper limit first. So when x is 5, you take the 5 and you plug it into this formula here for u. So u is equal to 5 over 2. So your upper limit becomes 5/2. And then when x is 3, you take the 3 and plug it into the formula. So u is equal to 3 over 2. So your lower limit is 3 over 2. And this is where it gets quite interesting because we're integrating with respect to u, and our limits are 3/2 and 5/2. Those are all numbers bigger than 1. That means that u is a number bigger than 1. So the absolute value of u is bigger than 1. So we're using this formula here. So now we can apply the formula. This 2/4 reduces to 1/2. And this is going to be the inverse of the hyperbolic cotangent of u. And there is no plus c because it's a definite integral. So instead I'll put a bracket, and let's indicate that these are u values just to be really clear by writing u equals 3/2 and u equals 5/2. Just optional step for added clarity. All right, so now we just plug everything in. So running out of room, so I'm gonna come over here. This is equal to 1/2, plugging in the 5/2 first. You get the inverse of the hyperbolic cotangent of 5/2 minus 1/2. Then here you get the inverse of the hyperbolic cotangent of 3/2. And we should probably just leave it like this. This is probably good enough. I hope this video has been helpful to someone out there in the world who's trying to learn some calculus. Good luck.